In this video, I'm going to talk a little bit about writing what are called particular equations of functions. The idea here is you're going to be looking at a picture and a graph may appear to be a certain type of function. Now that doesn't necessarily mean that that's the only possible function, but based on the appearance of the graph, it meets the requirements to fit some of the different categories we've discussed, okay? And so the first example here, this is a linear function, okay? It's designed to be a linear function. And specifically, we know it goes through the point 2, 1, and we know it goes through the point 4, 7, okay? There are a bunch of different ways to do this, okay? Honestly, most of the time, in most high school courses, when I write an equation of a straight line, I use the point-slope equation. If you remember, point-slope form is y2 minus y1, y minus y1 equals m times x minus x1. Okay, you need to know that basic equation. And you should be able to calculate the slope and just substitute everything in. So in this particular case, slope, of course, is the change in y over the change in x. Change in y is 7 minus 1. The change in x is 4 minus 2. So in this particular case, the slope is going to be 6 over 2, which is 3. Okay, so we can substitute that in for our m value. And then at that point, you can put either of the other 2 points in. So for example, when x is 2, y is going to be 1, and then I could work out my equation. So right now I have y minus 1 is equal to 3 times x minus 2. If you wanted to put it in slope-intercept form, you could. You could add 1 to both sides. Y would be equal to 3 times the quantity x minus 2 plus 1. You could multiply out the parentheses. You could go from there. I think in this particular case, it's going to be y equals 3x. I think it's minus 5 is the final equation. And I would check one of the points, okay? For example, if I put 4 in, do I get 7 back? 3 times 4 is 12, minus 5 is 7. Checks at least with that one point, okay? So that's probably the most obvious way. Now, there is a second approach, and I'm going to mention it for a reason because it's going to tie into some of our other approaches. The other route would be to go back to kind of our general form of the equation, okay? The general form of a linear equation, or at least one of the general forms, is the slope-intercept formula, y equals mx plus b, okay? Remember that if a point's going to be on a line, you've got to be able to sub in the x to get that y. So in other words, when I put in 2 for x, I should get back a 1 for y, okay? So that tells me that 1 has to be equal to 2 times the m value plus the b value, okay? Now that's an equation with 2 variables, but if I can come up with a second equation with 2 variables, then I can solve that system. And so you can come back and you can say, well, all right, when I put in a 4 for x, I want to get a 7 back for y. And that tells me that 7 is going to be equal to 4 times m plus the b value. That's not a terrible system to solve, okay? If you subtract these 2 equations, for example, 1 minus 7 is negative 6, 2m minus 4m is negative 2m, the b's would cancel. You find out that m is equal to 3. And by the way, you could have shortened it down a little bit by finding the slope, filling in that m value right off the bat, and then substituting in one of the points. But my point here is we're really just trying to find an m and a b. And since we're trying to find 2 values, if you can write 2 equations, you should be able to come up with a solution, okay? Again, how would I do it? Point-slope form. But I just want to make the point, you could do that. All right, now, second one. Let's say I want to write the equation of the function that passes through the points negative 2, 11, 1, negative 1, and 3, 1. All right? On the surface, you think, well, okay, what kind of function is this? This could be lots of things, okay? You could have a trig function that passed through these points. You could have some kind of, S-shaped cubic function that went through those points. There are lots of things it could be, okay? 3 points is not just going to guarantee what kind of function you have, okay? But let's say that the picture was drawn looking something like this, okay? And act like this is actually going through all those points. So maybe you look at the picture and you think, this kind of looks like a parabola, okay? Let's say that I wanted to write the equation of the quadratic that passed through those 3 points, okay? I'm going to go back to the general form. And by the way, notice here, it doesn't look like I have the vertex. So the vertex form, where you're filling in the x shift and the vertical shift and that kind of thing, you're probably not going to be able to do that, okay? But I can come back to the general form, okay? The general form is y equals ax squared plus bx plus c. There might be an x squared term, might be an x term, might be a constant term, okay? Notice, I need to find three values. I need to find a, I need to find b, and I need to find c. Well, guess what? I have 3 points, okay? 3 points means I have enough information to write 3 equations, which means I should be able to write the equation of this relatively easily using a 3-variable system, okay? So all that's gonna happen here is, when I put in -2 for x, I wanna get back an 11 for y, okay? So I wanna get back an 11 for y when I put in -2 for x. So that would be a times -2 squared plus, put in -2 for x, that'd be b times -2 plus c, okay? When I put in 1 for x, I want to get back a -1 for y. So y is -1 when x is +1. 1 squared plus 1 times b plus that c value, okay? And then when I put 3 in for x, I want to get back a 1 for y. So y is going to be 1 when I put in a 3 for x. Okay, that's going to be a times 3 squared plus b times 3 plus c, okay? So I end up with the following system. I get 11 is equal to 4a minus 2b plus c. -1 is equal to a plus b plus c. That's a nice equation there. And +1 is equal to 9a plus 3b plus c. Okay? Hopefully you've watched my video or you just remember from Algebra 2. Remember that you can solve a 3-variable system using matrices. So you should be able to rewrite this as the matrix 4, -2, 1. Those are the coefficients of the variables. 1, 1, and 1. And is that really? Yeah. And then 9, 3, and 1. Okay? And you should be able to fill all of that in your calculator. That we could maybe call matrix A. You're multiplying by a variable matrix. We have A, B, and C variables we're trying to solve for. And we want to get a result of 11, -1, and 1. Okay? So remember how this works. You've got, maybe call this matrix A times matrix X is equal to matrix, we used capital B before. So if you remember the whole idea here, if you have this equation A times X is equal to B, you're trying to solve for the variable matrix. I'm trying to get this equaling some values. So I can multiply both sides by the inverse matrix A inverse. Okay, the inverse will multiply by the original to give me the identity matrix, which leaves me with just x. I'm really taking the inverse of the coefficient matrix and multiplying it by the answer matrix. Okay, and so anyway, if you put all that in your calculator, hopefully you remember how to do that, or hopefully you've watched that video. Once I go run those numbers, we can see here that we should end up with the result of matrix A, B, and C being equal to 1, -3, and 1. Okay? Remember what those are. Those are the coefficients in the original equation. It's ax squared, so that's going to be 1x squared, plus bx, okay, so that's a -3x, plus c, and c in this case is 1. And that's your final equation, okay? This is called the particular solution, okay? Instead of a general equation, this is the particular solution. This is the particular equation that matches that set of data for a quadratic, okay? Now, you could have some other kind of curve that you write an equation that also passes through those 3 points, but this is the unique quadratic that would pass through those 3 particular points, all right? I'm gonna look at exponential and power functions in a separate video a little bit later.